Good afternoon, everyone. Welcome to the first session of our Introduction to Quantum Machine Learning workshop. First of all, we would like to thank our lecturer, Sinan Kalkan, for accepting our invitation. In this session, our lecturer, Professor Kalkan, will talk about generative adversarial network and autoencoder. I will briefly introduce our professor and give the floor to him. I would like to remind you that all the sessions will be recorded. Dr. Sinan Kalkan received his bachelor and master degrees from Middle East Technical University, Computer Engineering. He completed his doctorate at the University of Göttingen, Germany. After working as a postdoctoral researcher at the University of Göttingen and METU for a while, he joined METU Computer Engineering Department as a faculty member. His main research focuses on computer vision and machine learning. So, the floor is yours. Here.
Thank you for the nice invitation and the amazing workshop. For those of you who may not know the whole program, so this is part of a series of seminars and a workshop, and this is the first session. So this is a workshop on Introduction to Quantum Machine Learning. Today, we won't be talking about the quantum aspects of things. So we'll just introduce some methods that are used actually without any quantum computing or computer. In the next sessions, some libraries will be introduced pertaining to quantum machine learning, and the quantum versions of the models that I'm going to present today are going to be covered actually in the third session, in the third day. So if you want more information about the workshop and the following seminars, you can check out this webpage. Okay, so if we continue with my talk, we will look at the two very commonly used models, autoencoders and generative adversarial networks. Before that, maybe I can briefly talk about my background. I am interested in computer vision and machine learning, especially object detection and mitigating some problems in deep learning. I'm affiliated with several research labs. One of them is Image Lab, where we focus on different computer vision and pattern recognition problems. I'm affiliated with a robotics lab in METU, which is now part of a robotics center. I will skip through these details. So this is a really nice facility. I have been, for the last couple of years, working on different aspects of computer vision, machine learning, and robotics. Now I'm working more on computer vision and machine learning, but there are still very interesting problems, projects that I'm partially contributing to. One of the problems that I've been working on is context. How can we model context and use context for different problems? So, the context can be really critical for different problems. So if you, for example, look at this small object here, by just looking at the object or the small neighborhood around the object, it is not possible to understand what this object is. When you provide some context, some more region around the object, then we get more context, and we may try to understand that, okay, maybe this is not an egg, but it might be a ball. When you provide the full context by looking at the other objects in the environment, actually we can disambiguate this object and understand that it is a tennis ball. Without using context, existing models would say that, okay, this is, by just looking at this object here, existing solutions would say that, okay, this is a lemon or an egg or another object. But by providing context in an appropriate manner, we can actually resolve the ambiguity and understand that this is a tennis ball. Another line of my work is regarding object detection. In object detection, we are interested in identifying objects in an image and placing boxes around the objects. So for this, we have proposed several novel solutions published at top venues in AI. And in deep learning and machine learning, we are generally working with real data sets, realistic data sets, and in realistic data sets, it's often the case that the samples follow a long tail distribution. So some classes have actually more samples than other classes. This distribution, this long-tailed nature of the long-tailed distribution is problematic for us because the methods that we use for training deep networks are sensitive to this, and as a result, the deep networks that we train perform better on classes or categories with more samples, and they generally underperform for classes or categories with less number of samples. So this is called class imbalance. It's actually one of the many imbalance problems in deep learning, and we have been proposing novel solutions for this problem and studying this in a broader sense. Another interesting problem that I've been focusing on is bias and fairness. So we are interested in using deep networks in real life settings where, for example, we want to have a model that can recognize individuals from their facial images. So if you look at existing solutions, we observe that actually such models have bias towards certain demographic groups. So they can be, for example, working really bad. They can have really high recognition error rates for certain demographic groups. So we call that bias. So there are different sources of this, and we are, of course, to be able to use such networks, such solutions in real life settings, we need to solve this problem. So we cannot have models that have bias in their predictions. So we want to obtain fairer solutions and deploy fairer solutions in practice. So we have been working in collaboration with University of Cambridge. We have been working on some novel solutions for this. Another interesting problem is to enhance interaction capabilities of an industrial robot arm. So in factories, in assembly lines, we have such robots that are collaborating with humans, or they are maybe without collaboration with humans. They do certain tasks. So we are working on extending the capabilities of such robots so that they first appear more animate to us, so that instead of working with a robot that feels really cold, very difficult to work with, we can actually add simple behaviors to such robots so that they appear easier to interact with. Apart from this, we use machine learning methods, namely reinforcement learning, to make sure that such a robot can learn to assemble objects without using any supervision. So in a simulated environment, we can have object parts. We can tell the robot how the assembled object is going to look like, and the robot can by itself learn to assemble the objects. And with that learned assembly plan, the robot can watch the current assembly being performed by a human worker, and the robot can match the current state of the assembly to what it has learned, and based on that, it can make recommendations. If there are errors, the robot can identify the errors and suggest corrections. And another use of machine learning is actually to reduce energy consumption in buildings. So buildings are the most important users of energy, consumers of energy, and to be able to reduce energy consumption. One of the good starting points are actual buildings, residential buildings. So for this, to be able to determine how we can do that, we need actually methods that can predict, that can tell us the reduction in energy use if we change, for example, the insulation settings of buildings. Like, for example, if we change the windows so that they are more insulating and the energy, then what would be the gain? So normally this is done using physical simulations, which are really slow. And a recent trend is to use machine learning for this purpose. And we have been one of the leading researchers that use machine learning for such purposes. Okay, so after this introduction about what I'm working on, and maybe we can continue with the topic of today's talk. If you are interested in any of the problems, projects that I've described, if you have any questions, please let me know. You can reach out to me via email, and we can communicate about the projects. So today we are going to talk about autoencoders, and in the third session, a quantum version of this will be introduced, and we will talk about generative adversarial networks. And to better link these two models, I will introduce another model here, called variation autoencoders. Okay, autoencoders are actually one way of learning representations, or the manifold of a problem. So in general, we are working with data sets. So we have, let's say, a set of images. If you are looking at, for example, a facial recognition problem, we have images of faces. If you look at the samples of your problem, you would see that there is some structure. There is some structure, and then we are trying to inherently first identify that structure and learn a label or a number from that structure. So we call that structure the manifold. And in manifold learning, in representation learning, we are trying to discover that manifold. And if we can do that, if we can learn the manifold, then actually that means we can we can obtain a very simple linearized version of the manifold, from which it becomes very easy for us to analyze the data, analyze the samples, and learn a mapping to a discrete set of labels or continuous set of labels. Right. So there are many approaches for doing this. Autoencoders is just one of them, and for a long while, people have been working on alternative approaches for this. In the interest of time, we won't be able to talk about these, so we will just focus on autoencoders. Autoencoders can be named as an unsupervised learning method, in which we don't assume that we have the labels, target labels for the samples. So we just have the samples themselves. We don't, without using any labels, we can try to learn a manifold representation. This is also called the dimensional reduction technique, because in general, we have an input, we pass that input through a bottleneck layer whose dimensionality is in general less than the dimensionality of the input. And in an autoencoder, from this lower dimensional representation, which we call sometimes a hidden representation, sometimes a latent representation, from this hidden representation, we are trying to via a decoder, we are trying to reconstruct the input itself. So we provide the input is encoded to this hidden representation. And from this hidden representation, the decoder is trying to reconstruct the original input. So we have the input, we use the input as the target for supervising the autoencoder so that the reconstruction and the input are the same. And we can easily do that by using various loss functions. And we are trying to minimize this reconstruction loss or error, and we are updating the parameters of the network such that the encoder and the encoder can encode the input into a lower dimension space, and the decoder can decode the original input from this lower dimensional representation. Because the dimension of the hidden layer is less than the dimension of the input, we can call this as a dimensional reduction technique as well. If you have any questions, I guess there are some questions in the chat. Okay, there are not questions. Okay, if you have any questions at any point, just please type them in the chat box. Okay, so what would this give us is, so if your inputs are, for example, such samples where you have one hot representations here as the input, and you are trying to reconstruct them at the output, the network actually can learn, the autoencoder can learn to represent these inputs in this way. So in three neurons, in a three-dimensional space, these are the values that the autoencoder can produce. So you see that, for example, this is represented by a value close to 1 and 0, 0. So in a sense, we can maybe approximate this as 1, 0, 0. And this is something like 0, 1, 1. Maybe this is 0, 1, 0, 1, 1. Maybe this is 1 as well, etc. So you see that the network has learned to encode the information in a compact manner in such a way that the original input can be recovered from the compact hidden representation. So this is a really neat mechanism.
So for the correction, we have one question in Q&A box. How do you represent the manifold connections on input, if there are any?
Manifold connections. So the connections between different different samples, you mean. If that is the case, then actually once you have the manifold, you can look at samples that are similar to each other using a suitable distance measure. Then with that, actually, you can identify the neighboring points in the manifold. Otherwise, autoencoder itself doesn't provide that. I hope that answered the question. Okay, so we can implement autoencoders in different ways. So I will briefly explain the vanilla version, in which this encoder is actually a linear layer followed by nonlinearity, and decoder is a linear layer often followed by a nonlinearity. So here I have provided this in a more formal manner. So we have our input, we have a linear layer, so we multiply our input with a matrix of parameters. Assume that the bias is included here, and we have a nonlinearity applied on the linear layer. So this is the hidden representation whose dimensionality is less than D. And the decoder receives the output of the encoder, which is actually the hidden representation. A linear layer is applied on that. So we have a matrix W2 of parameters that are to be learned. And we have another nonlinearity. In some cases, we can skip nonlinearity. I will briefly talk about them. So this is a very simple autoencoder, and this can be implemented very easily. So in PyTorch, you just have a fully connected layer followed by a nonlinearity, and the decoder is fully connected layer followed by a nonlinearity. And for reconstruction loss, of course, depending on different settings, what your inputs are, you may have to change this, but in general, you can use, for example, squared error loss, and everything is differentiable. So you can use PyTorch's AutoGrad facility. So you can just try to minimize this by updating parameters, parameter matrices W1 and W2. And you can use, of course, gradient descent. Depending on the range of values in our input, we can change F1 and F2. If your inputs are, for example, real valued, then, and if you want to especially obtain a hidden representation where the values in the representation are bounded between 0 and 1, then you can use a sigmoid applied on the linear layer in the encoder. And for the decoder, we shouldn't use any nonlinearity because our inputs are real valued. But if you can normalize your inputs, then here in the decoder, you can use an activation function as well. And you can use a squared error loss here. If your inputs are binary valued or between 0 and 1, then for the encoder, you can use sigmoid activation function. And for the decoder, you should use sigmoid as well. So because the output values should be bounded between 0 and 1. And in this case, as the loss, you can use cross-entropy loss. So with an autoencoder that is trained in this fashion, we can learn actually a function that maps the inputs to a lower dimensional space, which we can use as a feature vector. So this is a compact representation of the input. But in general, the problems that we are working on are very complex, and one layer is maybe insufficient to obtain useful features. It might be that we need multiple layers of processing to be able to obtain useful representations for our problem. To be able to address more complex problems, what we can do is we can train an autoencoder in this fashion. So we can train an autoencoder, and after this autoencoder converges, we can remove this decoder. Then we would have a mechanism that can map the inputs to this manifold. Then we can take these representations for our samples, for our inputs, and train another autoencoder on top of that. So the hidden representations that we have obtained after the first autoencoder now actually are being used for training another autoencoder. Right, so we have a second autoencoder. After this second autoencoder converges, then we can again drop this decoder of the second autoencoder. Then we can use these hidden representations to either train another layer of hidden representations, another autoencoder, or if you believe that it is sufficient, then you can actually, for the downstream task that you have, which may be a classification task or a regression task, now we can use actually those representations and train a linear layer to solve that task. And you can combine everything. So this is coming from the first autoencoder. This is coming through the second autoencoder. This is coming through the supervised learning that we have performed here. And we can concatenate them, and everything is differentiable. We can use the learned weights through these for these layers, and we can fine-tune the whole network for the downstream task for which we have labels. Right? So this is especially useful in cases where the amount of labeled data is really low. So if you have lots of unlabeled data and only small amount of labeled data, this is a very neat idea. With the unlabeled data, we can actually use autoencoders to learn layers which can give us useful representations. And once we believe that the number of layers is sufficient, we can actually add a layer for the downstream task we have, which can be trained using the small amount of data we have, supervised data we have, and the whole network can be fine-tuned with the supervised data we have. So this is actually a useful technique if you have small amount of data. Although autoencoders are useful and they can learn actually useful representations here, people have identified over the years that the type of representations learned by the autoencoders can be quite different depending on the dimensionality of the hidden representation. So I will illustrate this via this set of simple patterns. So let's say we have these 4 patterns, one rectangle, vertical rectangle, horizontal rectangle, and an ellipsoid in a vertical position and a horizontal position. So one way to represent these set of shapes would be, and this would be actually learned by the autoencoder if you are not careful with the dimensionality of the hidden layers, is that one neuron would be representing just this shape. Second neuron would be representing just this shape. The third neuron would be representing just this shape, and the fourth one representing just this shape. So one neuron, each neuron is responsive to whole input. And this is generally not desirable in machine learning because we want neurons to be specialized to one part of the problem. So that the compositions of the different neurons, the responses of different neurons can actually solve the task for us. And there are several arguments about this being more more generalizable to unseen settings. So here we see that this neuron is just sensitive to this pattern, and if you provide a different pattern, then this neuron is not going to respond. And if you provide a novel input here that is slightly different from all of them, none of the neurons will respond. Alternatively, these 4 patterns can be represented by can be encoded by 2 neurons. So if we reduce the dimension of the hidden layer too much, then actually the autoencoder can learn such a solution. So if no neurons are active, that means, for example, this shape is provided, and for a different shape, this neuron is responding. For another one, this neuron is responding. For another one, these neurons are responding. So this is a possible solution, but again, this is very difficult to generalize. So by looking at the activations of neurons, it's difficult to reason about the specializations of these neurons. If you look at this scenario, this solution, we see that, again, we have these 4 shapes, we have 4 neurons, but unlike this case, for each pattern, multiple neurons are active. And if you look at that, if you look at these activations, so for these 2 neurons are active, for these 2 neurons are active, etc. And if you look at the activations, there is some pattern actually. By looking at the activations, we can easily deduce that actually this neuron is encoding the corneredness of the shape. So these 2, there is something common between these 2, and this neuron is capturing that. And that's common property is that these 2 shapes have corners. And this, for example, is common between these 2 shapes. If you look at what is common between these 2 shapes, you would see that actually these are both vertical. and these then would be encoding roundness. So we call these distributed over complete representations, or sometimes we call them sparse representations as well. And the nice property of such representations is that it is easier to learn from such representations because it can generalize easily to novel shapes. So if you provide, for example, a novel shape that is that's a circle, in these cases, a circle would not be represented by the neurons, but in this case, actually, this neuron would be active because it is round, and this neuron may or may not be active because it's not vertical, it's not horizontal, and so this is encoding roundedness. So this would be active, and these horizontal and vertical both would be active because the circle is elongated in both directions. So, and there are several justifications for having sparse representations from biological perspective as well. It appears that our brain is actually relying on sparse coding encoding mechanisms. There are several justifications for this. In the interest of time, I will skip these motivations. But we can say that it is, I can summarize the existing findings saying that it is easier to learn new mappings from sparse representations. And there are lots of theoretical justifications for this as well. And there are many empirical studies that show that the neuron activations in our brain in different layers actually suggest a sparse encoding mechanism.
I will drop again. We have a question in Q&A box. Are there any methods other than dropout that promotes distribution?
Sparse distribution, I suppose, is meant by the question. So I will briefly talk about the how we can ensure sparsity. Okay, so how can we enforce sparsity or complete distributed representations? It appears that using stochastic gradient descent is already making our representations more sparse. But if you want more sparsity, you can, in the literature, people have proposed different solutions. You can modify the loss function. In the case of sparse autoencoder, we add a penalty term such that the activations of the neurons are sparse, and each neuron activates only on a limited amount of samples. This can be performed in a hard manner as well in case sparse encoders. I don't have time to talk about them in detail. Or we can add some stochasticity to the samples or to the training dynamics other than stochastic gradient descent. One very good example is actually denoising autoencoders, which I will briefly talk about. In sparse autoencoders, we have a hidden layer which is actually larger than the dimensionality, which has more elements than the number of elements in the input. So the dimensionality of the hidden layer is bigger than the dimensionality of the input. Again, we can have a linear layer followed by a nonlinearity for the encoder and for the decoder as well. And in sparse autoencoders, what we do is actually we use different methods to enforce that the activations are sparse. One way of doing that is adding a regularization term on the weights such that most of the weights are close to zero. This then in turn ensures that most of the activations are in general zero. We can measure the we can accumulate the activation for a neuron over a set of samples, then we can penalize the total activation of a neuron during training. We can we can actually look at the distribution of the activations for a neuron, and we can try to make sure that this distribution is a peaky one. Using several measures, we can do that. And in the literature, this approach was studied more. What we do in this approach is that we, over a batch of samples for each neuron, for input and for samples in the batch, we look at the activation, we accumulate the activation, we take the average, and we try to make sure that this average activation for a neuron over a batch of samples is actually bounded above by a small value. To be able to solve the encoding and decoding task with the constraint that the activations for each neuron is actually bounded above by a small value, actually, the network has to learn, the network has to make sure that the activations are really sparse. Another interesting method to obtain sparse representations is denoising autoencoders. In the denoising autoencoders, again, we have an idea similar to autoencoders. We have an input. We are trying to reconstruct the input at the output. But this time, to the network, we don't provide X, we provide a corrupted version. We add white noise, for example. If you have images as the inputs of the autoencoder, you add white noise, or you flip the bits, the pixels, sorry, or you set the pixels to 0. So you can think of different ways to corrupt the input. You provide corrupted input to the encoder. We have a hidden layer where we have the useful hidden representation, and from this hidden layer we have a decoder that tries to reconstruct not the corrupted one, but the original uncorrupted input. Right, so this is a more difficult task. So we have a corrupted image, let's say, and from the corrupted image, we are trying to recover the original one. So to be able to recover the original image where the noise is removed or masked pixels are recovered, the encoder and the decoder needs to make sure that the different relations between different pixels, different parts of the input are taken into account for encoding the input and for decoding or reconstructing the input. So this turned out to be actually a very powerful trick for learning useful representations. What it does, in a sense, is that, so let's say we have an original input, so we corrupt the input, and the network actually learns to represent the samples in such a way that actually such a corrupted input actually is represented by its a suitable version, or sorry, not this one, the original uncorrupted version. So this makes the representation function very robust to noise in the data. Although this was originally proposed for learning useful representations, people actually used the same idea for making their networks more robust to noise and perturbations in their scenarios, in their applications. For example, you are training again a network for recognizing faces. If you want your network to be very robust to, let's say, some noise or blur or light changes in the real world environments, then actually during training, on top of your images, you can add artificial light distortions or blur distortions, and you can provide the corrupted image to your network so that from the corrupted image, actually it can learn the problem. It can learn to solve the problem. Okay, that was autoencoders. Before we talk about variation, the generative adversarial networks, I want to talk about the variational version of autoencoders. It will better motivate our coverage of generative adversarial networks. In autoencoders, we can use an encoder to encode, let's say, an image into a compact representation, lower dimension space here, from which the original input can be recovered, reconstructed. In many cases, we want to be able to make modifications in this representation such that those changes, so let's say I want to modify this value. And by modifying that value, I want some aspect of the input or the image to be changed. For example, I want the color of the cat to be changed, or I want eye color to change, or the mouth to close, etc. So autoencoders, this is not possible. So if you make a change here and provide that updated value to the decoder, it's just going to provide something random, and it may be totally different from the input. This actually, the ability to be able to change this and the network to generate something that corresponds to something different that corresponds to the change we performed here actually requires an understanding of the distribution of samples and or distribution of the hidden representations here. This is addressed by variation autoencoders. So in variation autoencoders, we are trying to learn the distribution of the let's use Z to denote the hidden values. And in variation autoencoders, we are interested in learning the distribution over the hidden vectors, such that when we make such a change, actually, while staying in this distribution, there is a meaningful effect is observed. So this is, of course, difficult. So I will skip this part. This is not really critical. So this is difficult because to be able to train such a network, we need to know the probability distribution of the samples, which actually is intractable, or the distribution of the hidden values given the samples actually is, for the same reason, intractable. To address this, to mitigate this limitation, people over the years came up with the idea of approximating this probability with a deep network, such that the network has parameters. The parameters can be learned, and via a very simple trick, this network can be trained. So normally this is Z. You would be interested in modeling the probability of Z given X. And this is intractable. We are trying to approximate this by a network parameterized with phi. And we are trying to approximate and make sure that this Q approximates this probability distribution, which is intractable. To make sure that the approximation is close to the probability distribution that we want to approximate, we can use Kullback-Leibler divergence. We want to minimize this. If you open this up, you would see that there are three terms. This term is intractable because we cannot easily calculate this, but this is constant. Observing that this is constant, we can rewrite it like this. So this is constant. And we want to actually minimize this. But again, we cannot calculate this part because it is intractable. But if this is constant, and if we want to minimize this, actually maximizing this would work as well. So if this is constant, maximizing this would mean actually this is minimized. So then I don't need to directly minimize this. I can just maximize this. And this is called evidence lower bound. And this can be, both terms can be calculated. So this is the trick we use in variation autoencoders, and this is how we can train a network a network which provides us actually a probability distribution over the latent space in such a way that we can make some changes here, and those changes will actually have a meaningful effect on the image. So we can actually generate novel samples. So with this, actually, we switch to a solution, a network that is generative, that can generate novel samples. And with that, we can look at a prominent pioneering example of a network that can generate novel samples, which is called generative adversarial networks. This was proposed in 2014 by Ian Goodfellow. Actually, if you read the stories, Ian Goodfellow says that the idea started in a pub. So they were having a discussion with other researchers, AI researchers, and they were discussing whether they can use deterministic networks to generate novel samples, such that the qualities of the novel samples are really convincing. So his friends, fellow researchers, didn't believe in the idea, and Ian Goodfellow went back home that night and spent the whole night implementing his idea, and in the morning he had a working version. So he implemented and it worked without any problems. And he said that if it hadn't worked, he wouldn't have continued working on that, and actually generative adversarial networks probably wouldn't have existed. But luckily, it worked, and a really exciting line of approaches, family of models emerged as a result. So let's talk about what again is how it works. So the idea is slightly different to variational encoders. This time, in variational encoders, from the image we have an encoder. We try to obtain a latent representation, and the decoder then reconstructs the input, right? So we have an encoder and a decoder. In a GAN, we directly start with a latent representation. So sometimes we also call it a noise vector that follow a certain distribution, and we have a deterministic network, a CNN, for example, which you call as the generator. The generator maps the noise vector, the latent representation, to an image. So it generates an image from a certain noise vector. Of course, initially the weights of the generator will be random, right? And the image that has been generated by the generator will be garbage, right? So it's not going to look like anything meaningful. But we can actually train another network called discriminator. Again, this can be a CNN, for example. And we can train a discriminator such that it can distinguish a fake image that is generated by the generator and a real image that we already have. So we know that these are real. We know that these are generated by the generator, so they are fake. We can train the discriminator such that it learns to distinguish whether the provided input, provided sample, is fake or real. So this is a binary classification, right? So, and we can train the discriminator, and since everything is differentiable, we can provide gradients all the way from this discriminator to the generator to make sure that the generator can generate samples that can fool the discriminator, such that the images generated by this generator can be recognized as real by the discriminator instead of fake. Right? Once that can be done, once the generator can fool the discriminator such that the generated images are perceived as real by the discriminator, then actually the quality of the generated samples are actually convincingly good, so the discriminator cannot distinguish them. Right. So that is the general idea. So see, we have two networks that are working in an adversarial fashion to each other. One is the adversary of another one. That's why we call these generative adversarial networks. So the training objective is very simple. So we are trying to train the discriminator such that on real images, it can recognize the real images as real. And the images generated by the generator, these are fake, it can recognize them as fake, right? So it's trying to, the discriminator is trying to maximize this and these two terms. Whereas the generator is trying to fool the discriminator, and this is possible by trying to minimize this. So generator is trying to minimize this objective, whereas discriminator is trying to maximize these two. Right? So this is the recognition loss, not loss, objective. For on fake images, we are trying to, the discriminator is trying to maximize this. The generator is trying to minimize that. So if you look at the training dynamics of a generative adversarial network, you will see that throughout training, actually, the different adversaries interact in an interesting manner. So let's say this is the true distribution of the data. And here, this is the distribution that is currently generated by the generator. And this is the response, let's say, of the discriminator. Right, so we are trying to map Z, the noise vector, to the space of X, the images, let's say, such that the discriminator cannot distinguish between these two distributions. And our aim is to make sure that the generator can generate samples such that the distribution of the samples is actually overlapping with this one. Initially, the weights are random, so generator will generate something random, and the discriminator will have difficulty because it started with random parameters at the beginning. So, but very quickly it will start to distinguish the samples of the real data shown in black dots from the fake ones. And it can provide 1 here, saying that it is real, and it can easily say that, okay, it is 0 here, so it is fake here. So the discriminator's job is really easy at the beginning. But since the generator is updating itself to make sure that the discriminator can be fooled, in time, we see that actually the distribution of the samples generated by the generator is getting closer and closer to the real distribution of the real samples. And in time, the discriminator's job will be more and more difficult, and at convergence, where hopefully the distribution of the samples generated by the generator and the distribution of the real samples are going to be identical, hopefully. At that point, the discriminator won't be able to distinguish between these two, and on average, it will just provide 0.5 probability. Although this is the ideal setting, the scenario that we hope for, in general, there are several challenges and problems with generative adversarial networks that I will briefly talk about. And the training dynamics, training loop is actually very easy. So at each iteration, we random sample a set of noise vectors. We can call them latent representations. And we get a set of samples from the real data. So in training again, we need a set of real data as well. And we update the discriminator by feeding the real data and make sure that the discriminator can recognize them as real. And the generated data, where we provide these noise randomly sampled noise vectors as input to the generator, and the discriminator tries to make sure that this is actually recognized, these are recognized as fake. So the discriminator is updated to maximize these two terms. And we have a set of noise samples. Again, we generate some images, and this time we are trying to make sure that the generated images can minimize the recognition probability of the discriminator. So we are trying to minimize this. We are updating the parameters of the generator so such that this is minimized. So we are maximizing this, we are minimizing this. So in an iterative fashion, actually, we can update the discriminator for a number of steps, then we can update the generator for a number of steps, and we can actually have a loop over these iterations. So if you look at the earlier samples generated in this fashion, nowadays such artificially generated samples look very simple, very noisy. They are low resolution, and we can easily understand that they are generated. And now in a few slides, we will see that the state of the art is actually different, but this is how things started. And back then, actually, these were state of the art results. But these are generated numbers, these are generated images, novel facial images. So these are very noisy, but in time, we see that things develop very quickly, and we have now models that can generate very realistic images. One problem with GANs is that if our data has multiple modes, then once the generator can learn that one of the modes can learn a mapping weights such that it can get a good reward from the discriminator for one of the modes, then actually it will try to map the whole latent space to one of the modes, and it will discard the other mode. This is called mode collapse problem in GANs, and over the years, people focused on using different techniques to avoid this. A common strategy is to use actually a different loss function. And the original GANs, the GAN model was a big, had a big impact in a short amount of time. Actually, extensions have been proposed. One extension is to use convolutional layers instead of fully connected layers, which was the case in the original paper. Then people realized that actually, in addition to the noise vector, we can provide some conditions here, and we can generate images that satisfy those conditions. So I can, for example, here say that I'm trying to generate a male image. And if I provide as the real image here, images of real images of male people, then actually this the generator can learn to generate male images such that its discriminator can be fooled. So this turned out to be really successful, and in a short amount of time, people actually extended these methods such that instead of providing a single label as a condition, we can provide a whole text, and we can generate an image here that corresponds to, that satisfy such a text. And these are samples, for example, that can be generated if you provide such a text to a conditional GAN model. And a few years back, this was the state of the art. So the method was called style GAN. And these are the images that were generated using a style GAN. And if you look at the images, and if you compare those images with the first images that were generated by the first GAN model, there's a huge gap, and it's visually, it's not possible for us to understand that these are generated. If you look at the solution they use in style GAN, They had a very deep network. First, given the noise vector, they obtained an intermediate representation, actually a weight representation, and they used these representative for modulating a multi-layer decoding step. So at multiple layers, we slow by slow, step by step, uh, um, generate the image at a finer detail. First, we start something with something more noisy. Then in the next layer we make it less noisy. In the next layer we make it less noisy, and while doing so, we may increase dimensionality, and this turned out to be really effective. And this paved the way for more recent, more capable models called diffusion models. Where in diffusion models, from a noise vector, we have a step-by-step approach where we denoise the representation, and step by step we obtain a representation which is noise free and very high resolution and very has high fidelity. So if you compare that to variation autoencoders and variation autoencoders, from the input we have an encoder, we have a latent representation here from which we can reconstruct the input. This is used for training the encoder. And for GAN, we start with a noise vector. We have a generator that can generate a fake image, and a discriminator can actually learn to distinguish between a fake image and a real image. In the case of a diffusion model, we have a step-by-step procedure, which is maybe more difficult to train, but the images that we can generate in this fashion are really impressive, really amazing. So these are images generated using Midjourney, a very popular diffusion model that can be conditioned with textual prompts. You see that these are very impressive. So the original GAN model that was proposed in 2014, and after that 9 years have passed, and this is in a really short amount of time actually we have progressed very significantly. Okay, so with this maybe I can conclude. So in this 1 hour, in this short session, we talked about autoencoders, how they work, what they try to achieve, and different types of representations we can hope to learn in an autoencoder. And we looked at a variation version of this, which could allow us to generate actual novel variations of the input. So we can make changes in the latent representation, and those latent changes can have a meaningful effect on the reconstructed images. And we talked about generative adversarial networks, which is a more well-known method for generating samples. But nowadays, as I said, the state of the art is with diffusion models. Okay, thank you for listening. So I guess there's another question.
Yes. Is this the same technology used in stable diffusion?
Yes, that's the case.
I would like to ask our participants if they have any other questions.
You can also reach out to me if you have questions after the session. I will be happy to help and provide pointers for your questions. So these models have been studied a lot, and there are many different implementations of these available in different frameworks, PyTorch, TensorFlow, etc., at different levels. So we can, if you are interested, I can also send you pointers. But if you just Google autoencoders in PyTorch, you will see lots of helpful pages and implementations. I hope it has been helpful.
I would like to thank you once again for your time and valuable contributions. And I would also like to thank our participants for their participation. And hope to see you in the following sessions that will be held on Wednesday and Thursday on quantum neural networks, quantum encoder, and quantum generative adversarial network.
Okay, thank you.
See you.
Have a nice day. Bye.